In 1854, there was this single, truly terrifying map of water pumps and cholera deaths. And it did what, no medical professional of the time could actually do.
Right, the John Snow map. He plotted the exact locations of the deceased and proved the disease was spreading through a contaminated public water source.
Exactly, completely debunking that whole prevailing theory of foul air. And that document wasn't just some grim drawing for the archives, It was arguably the birth of modern spatial analysis.
It really was. And have you ever looked at a modern digital map and realized it holds that same immense analytical power, just, waiting to solve your most complex problems?
Welcome to today's deep dive into the absolute mechanics of spatial data. Our mission today is to map out the exact journey of taking raw, unorganized geographical information and turning it into crystal clear, actionable answers.
Because we usually think of geography as something fixed, right? We treat maps like static posters on a wall where boundaries and roads never change.
Right, like they're just pictures.
Yeah, but the reality outlined in our documentation is that Geographic Information Systems, or GIS, transform those static lines into a highly active mathematical engine.
You're no longer just looking at where things are located on the Earth. You're actually using complex algorithms to discover hidden relationships that are completely invisible to the naked eye.
Exactly. And we are going to walk step by step from defining a real-world problem to visualizing the final map, strictly following the detailed technical workflows provided in our stack.
And along the way, we're going to dissect two powerhouse software platforms, the commercial giant ArcGIS Pro and the open source champion QGIS.
But to understand the power of these platforms, we really have to start with the foundational blueprint detailed in the notes.
Because jumping straight into downloading data without a clear question is, it's just a recipe for getting completely overwhelmed.
Oh, absolutely. A typical GIS workflow does not begin with opening the software. It follows a very strict logical sequence.
Right, so it starts with defining the problem, then collecting spatial data, preparing that data mathematically.
Then performing the actual spatial analysis, visualizing the results, and finally, sharing the maps or reports.
I want to focus on that very first step for a second. How specific does this initial problem definition actually need to be?
It needs to be incredibly specific.
So if I'm a city planner, is it enough to just ask, how do we improve public transit?
No, that is far too broad. Asking that will just result in you downloading terabytes of totally useless data.
Just clogging up your hard drive.
Exactly. The documentation emphasizes that you must frame the question with strict geographic and conditional parameters.
Okay, so what does a properly defined problem sound like then?
It sounds more like which specific bus stops are located within 500 meters of an elementary school and currently have no covered shelters.
Oh, wow. Okay. Yeah, that level of specificity is fascinating because it immediately acts as a filter for what files you actually need to source.
Right. You suddenly know exactly what you're looking for.
You need a layer for bus stops, a layer for school property boundaries, and perhaps an attribute table detailing the shelter infrastructure.
Exactly. And that brings us to the actual nature of the files we are collecting. Because all of that spatial data you're gathering, it essentially falls into two distinct buckets.
Based on how computers interpret the physical world, right?
Right. So the first bucket is vector data, which represents discrete objects using points, lines, and polygons.
And the second bucket?
The second is raster data, and that represents continuous phenomena across a surface using a grid of pixels or cells.
Let's break down the underlying mechanics of vector data first, just to get a clear picture.
Sure, let's do it.
Because when we look at a vector map, we see a smooth shape, like the exact property lines of a real estate parcel or, the winding path of a river.
Right, it looks like a drawing.
But how is the computer actually storing that smooth, continuous shape in a database? It's not actually drawing it.
Under the hood, vector data is essentially a massive text file of coordinate pairs. That's all it is.
Wait, really? Just text?
Yep. A point is just a single x and y coordinate mapping longitude and latitude. And a line is stored as a sequence of those coordinate pairs, which are called vertices.
Okay, and those are mathematically connected in a specific order.
Exactly. The computer just connects the dots.
And so a polygon, like a school boundary or a city park, is just a line that eventually loops back onto itself.
You got it. The software reads that sequence of coordinates, notes that the first and last pair are perfectly identical, and it understands that it encloses a measurable area.
That method seems incredibly precise. Because it defines definitive starts, definitive edges, and definitive ends.
It is. That precision is exactly what makes vectors perfect for discrete objects with clear boundaries. Like a city road network or a tax parcel.
But the physical world isn't always composed of hard edges and distinct boundaries, right?
No, definitely not. You cannot draw a definitive vector polygon around a changing weather pattern or the gradual slope of a mountain range.
Which is exactly where raster data takes over. When our sources describe raster data, they compare it to a digital photograph composed entirely of microscopic squares.
That's a perfect analogy. If you zoom in closely enough on a raster layer, you stop seeing a smooth landscape.
You just start seeing individual pixels arranged in a massive grid.
Right. The mechanism here is completely different from vectors. A raster is a two-dimensional matrix of cells, much like a giant spreadsheet.
So the software knows the geographic location of the top left corner of the grid, and it knows the exact size of each cell.
Yes, so instead of storing thousands of complex coordinate pairs for every single shape, the computer just calculates the position of any cell based on its row and column index.
That's super efficient, but what information is actually stored inside those tiny squares?
Well, every single cell in that matrix holds a specific numerical value, and that value represents a condition on the Earth's surface at that exact location.
Like what kind of condition?
So in a digital elevation model, or a DEM, that value represents height above sea level.
Okay, I see.
Or in satellite imagery, the value might represent the amount of infrared light reflecting off plant leaves.
Oh, wow. And the documentation points out a critical relationship here. Your initial problem dictates the data type you need.
Yes, always. If your core question requires finding the steepest terrain in a mountain range to predict avalanche risk, you immediately know you need a raster data set.
Because elevation is a continuous surface.
Precisely. Conversely, if your question asks which specific bus stops are near those schools we mentioned earlier, you need vector data.
You don't need a continuous grid of the whole city's temperature or elevation for that.
Right, you just need vector points representing the exact coordinates of the stops. The spatial problem inherently defines the digital tools required to solve it.
So now that we understand the structural difference between vectors of discrete coordinates and rasters of continuous grids, we really need to talk about the digital workbench.
Yeah, where we actually do the work.
We have to load this data somewhere to perform our analysis. And the documentation heavily contrasts two industry standards, ArcGIS Pro and QGIS.
These two platforms operate in vastly different technological ecosystems.
Let's start with ArcGIS Pro.
Okay, so ArcGIS Pro is Esri's flagship commercial product. It's built entirely as a native Windows application.
And it's not free, right?
Oh no. It operates on strict named user licenses, which are usually tied into a larger enterprise-level architecture like ArcGIS Online or a dedicated corporate server.
Right. And on the other side of the arena, we have QGIS.
The open source champion.
Yeah. This platform is open source, licensed under the GNU General Public License, and it runs natively across Windows, Mac, and Linux.
That cross-platform ability is a big deal for a lot of users.
But what does that GNU GPL licensing actually mean for a user practically, compared to a commercial license?
Well, the GNU General Public License ensures that the software is entirely free to download, use, and modify. Like, there are absolutely no subscription fees.
It's amazing.
It really is. And more importantly, it guarantees that the core code can never be locked behind a proprietary paywall. The community of developers worldwide constantly audits, updates, and expands the software.
The documentation actually notes that ArcGIS Pro requires a virtual machine or a partition like Boot Camp if you want to run it on a Mac.
Yeah, that's a known hurdle.
That seems like a massive hardware hurdle for users who aren't on standard Windows Enterprise machines.
Yeah.
So if QGIS is free and runs everywhere, why would large organizations choose the restrictive, expensive platform over the flexible, free one?
It really comes down to institutional reliability and the demand for guaranteed accountability.
Like customer support.
Exactly. Large corporate enterprises such as national energy companies or metropolitan utility departments, they require professional service level agreements.
Oh, right. Because if things go down, it's a disaster.
Yes. If a critical spatial database managing a city's power grid corrupts at 3:00 a.m., they need a dedicated legally bound support hotline to call immediately.
That makes total sense. A major utility company can't exactly post a critical error log to a community message board, and just hope a volunteer developer replies by morning.
Right, they are paying for the safety net, they're paying for the professional certifications, and the seamless enterprise deployments across thousands of internal employee accounts.
Plus, the documentation mentions that ArcGIS Pro offers a deeply unified environment.
It does. It has advanced extensions for built-in 3D rendering, complex network analyst routing tools, and highly sophisticated spatial analyst capabilities.
And those are all engineered to work flawlessly together under one commercial umbrella.
Exactly. The ecosystem is closed, sure, but it is highly controlled and very stable.
But the documentation is also very clear. The QGIS is not just some secondary alternative for people without a budget.
Oh, absolutely not. It is a heavyweight champion in its own right.
Yeah, it's heavily relied upon by non-governmental organizations, academia, individual scientific researchers, and huge open data projects worldwide.
It's incredibly powerful.
But how does it handle complex analysis without those expensive built-in proprietary extensions that Esri has?
Well, QGIS relies on a massively extensible architecture. It's driven entirely by community plugins and integration with other open source libraries.
Can you give an example from the notes?
Sure. For example, it utilizes the Geographic Data Abstraction Library, or GDAL, right out of the box.
GDAL, okay, and what does that do?
This allows QGIS to support a staggering array of open data formats, things like PostGIS databases, GeoJSON, and GeoPackage, all without needing any special conversion tools.
Wow. And the technical notes mention that for actual processing power, QGIS interfaces directly with Python via PyQGIS.
Right, as well as integrating entire other analytical suites like GRASS and Saga.
So you aren't just getting one program. You're basically getting a central hub that commands dozens of specialized open-source mathematical engines.
Exactly. Meanwhile, ArcGIS Pro uses its own proprietary environment. It heavily utilizes ArcTIE, the .NET SDK, and Esri's Visual Model Builder interface.
Both approaches seem incredibly powerful, just different philosophies.
Yeah, exactly. Like a nonprofit researcher tracking deforestation might leverage the flexibility of QGIS, but a municipal zoning board is going to utilize ArcGIS Pro to enforce strict topological rules across a massive city database.
So, with the philosophical and structural differences of our software understood, the documentation moves us into the actual workflow.
Right, gathering the pieces.
Yeah, bringing our vector and raster files onto the map. But loading data is rarely just clicking an open button, is it?
No, definitely not. It requires surviving what the sources call the CRS trap.
The CRS trap, let's unpack that. The Coordinate Reference System, or CRS, is mathematically the most critical preparation step in any spatial workflow.
Yes, because the Earth is essentially a lumpy, irregular ellipsoid. It is not a perfect sphere.
Right.
And a CRS contains the complex mathematical algorithms required to flatten that 3D reality onto a flat 2D monitor or a piece of paper.
Let's walk through the initial loading process first before we dive into the math of flattening the Earth.
Good idea.
So in QGIS, you bring your data into the environment using the Data Source Manager. Or, alternatively, you navigate to the Layer menu, select Add Layer, and explicitly choose Add Vector Layer or Add Raster Layer depending on your file type.
Right, and in ArcGIS Pro, the interface is designed to be slightly more drag-and-drop oriented.
How much so?
You can utilize the Add Data button situated directly on the main map ribbon, or you can simply drag spatial files directly from the catalog pane and drop them onto your active map view.
And then the software instantly attempts to read the file's spatial metadata.
Exactly, but here's where the trap snaps shut.
Let's lay out this scenario from the documentation. Let's say you load a shapefile of your city's school districts, and its metadata says it is projected in EPSG.32633.
Okay.
Then you load a CSV spreadsheet of bus stops, but its metadata is in EPSG.4326. What do those codes actually mean?
So EPSG codes are standard registries that tell the software exactly which mathematical formula was used to map the data.
Okay, so EPSG.4326 refers to what?
That refers to WGS84, which is a global geographic system that measures locations using degrees of latitude and longitude.
Like the classic coordinates everyone knows.
Right. And EPSG.32633 refers to a specific UTM zone, which measures locations using entirely flat linear meters from a central meridian.
So wait, we have one layer measuring distance in angular degrees based on the center of the Earth, and another layer measuring distance in flat meters laid over a specific slice of Europe.
Yes. And if you try to view them together as they are, the software is going to experience a massive mathematical conflict.
So what happens? Do they just not show up?
Well, your bus stops might render literally thousands of miles away from your schools.
That sounds like a nightmare for a beginner.
It is, but to prevent users from panicking, both ArcGIS Pro and QGIS utilize a visual trick called on-the-fly projection.
On-the-fly projection. Okay, what does that actually do?
The rendering engine detects the mismatch and temporarily bends the display of one layer so it visually aligns with the other on your monitor.
Oh, so it just fakes it.
Yes. It creates the illusion that your data is perfectly synced.
And the documentation is very stern about this illusion. It warns that on-the-fly projection alters the pixels on your screen, but it does absolutely nothing to the underlying database of coordinates we discussed earlier.
Right. That text file of vertices we talked about, it remains entirely unchanged.
So if you attempt to run a spatial analysis, like calculating the exact distance between a WGS 84 bus stop and a UTM school building, what happens?
The software will try to execute math across two entirely different units of measurement. The resulting calculation will be completely invalid, producing garbage data.
And it might not even throw an error code. It just gives you the wrong answer.
Exactly. It's incredibly dangerous for spatial accuracy.
So how do we bypass the visual illusion and force the data into mathematical alignment?
The notes provide the exact clicks for this. In QGIS, you don't just tweak a display setting, you right-click the problematic layer, select Export, and choose Save Features As.
Okay, so you're actually saving a new file.
Right. From that menu, you browse for your target EPSG code and generate a brand new, permanently reprojected file.
And what about ArcGIS Pro?
The ArcGIS Pro workflow achieves the exact same mathematical transformation through its geoprocessing framework. You navigate to Data Management, Open Projections and Transformations, and launch the Project tool.
So you input your disparate data set, define a new output location, and explicitly define the output coordinate system.
Yes. And the sources also note a fascinating alternative for those who prefer bypassing visual interfaces entirely.
Oh, right. The command line tools.
Oh.
Specifically, GDAL's RGOJ utility can perform this matrix transformation instantly.
Yeah, that's for the really technical users.
Yeah.
You simply open your terminal and type a command like GIS HES areas EPSG.4326, followed by your output and input file paths.
That command line approach seems incredibly efficient for processing, like hundreds of files simultaneously.
It really is. But regardless of whether you use the QGIS GI, the ArcGIS Pro project tool, or the GDAL command line, the mechanical goal remains totally identical.
The software basically recalculates every single coordinate pair in the database using complex trigonometry, right?
Exactly. It ensures absolute mathematical consistency across your layers.
Okay, so now our schools and our bus stops are loaded, visibly aligned, and fundamentally sharing the exact same underlying coordinate reference system.
Right. They speak the same spatial language now.
However, as the documentation points out, the layers are still technically isolated. Like the school database has no idea that the bus stop database even exists.
Which means we have to move into the connection phase of the workflow. The true power of a geographic information system lies in its ability to make separate data sets communicate.
And the documentation categorizes these connections into two distinct methodologies: attribute joins and spatial joins.
Let's investigate the attribute join first, because the notes specify that this method does not actually rely on geography at all.
Yeah, that's interesting. It is fundamentally a standard database operation. So how does the software merge two tables without looking at where the features are located in the map?
An attribute join requires a shared key field, basically a column of identical data present in both tables.
Right, like an ID number.
Yeah. So suppose your vector layer of school polygons has an attribute column titled Districted D, and you also possess a completely separate Excel spreadsheet containing budget information, which also features a Districted B column.
So the software simply scans down both columns, and when it finds matching text strings or numbers like District 7 in both files, it locks them together.
Exactly. And it appends the budget columns directly onto the end of your spatial attribute table. The software never checks the coordinates, it only checks the text.
To execute this relational database function in QGIS, you open the layer properties of your target spatial file, navigate to the Joins tab, and click the Add button to specify your target layer and matching fields.
And in ArcGIS Pro, you right-click the target layer directly in the Contents pane, expand the Joins and Relates menu, and select Add Join.
That is incredibly useful for attaching census demographics or financial data to existing boundaries.
Oh, it's essential.
But what if we don't have a shared ID column? What if we just have a spreadsheet of thousands of bus stops, And we need to know which specific school district boundary they physically sit inside.
This scenario is exactly where we deploy the spatial join, which is a true geographic query.
Okay, so how is that different?
A spatial join ignores matching text fields entirely. Instead, it relies on complex spatial algorithms to compare the actual X and Y coordinates of your bus stops against the vertex boundaries of your school polygons.
The documentation mentions concepts like intersect and within for these joins. But how does the computer mathematically prove that a specific point is trapped inside a complex, irregular polygon? I mean, it can't just eyeball it like a human looking at a map.
No, it uses math. The software frequently utilizes a mathematical concept called the raycasting algorithm.
The raycasting algorithm, how does that work?
So, from the exact coordinate of the bus stop, the computer calculates an imaginary straight line extending outward to infinity.
Okay, an imaginary line to infinity, got it.
Right. It then counts exactly how many times that imaginary line crosses the vector boundary of the school polygon.
That is a brilliant piece of logic, because if the line crosses the boundary an odd number of times, the point must be trapped inside the shape.
Yes. And if it crosses an even number of times, the point must be sitting completely outside the shape. The computer runs this raycasting test for every single bus stop simultaneously.
Oh wow, that's incredibly clever math. And once the algorithm confirms which points are physically inside which polygons, it merges their attribute tables together based purely on that locational relationship.
Exactly. To run this in ArcGIS Pro, you navigate to the Analysis tab, open the Overlay toolset, and launch the Spatial Join tool.
And for the open source users, the QGIS workflow requires opening the processing toolbox and searching for the join attributes by location algorithm.
Right. Both systems handle the intense computational load of running thousands of raycasting checks in a matter of seconds.
But the documentation actually takes this concept of comparing geometries even further with overlays.
Yeah, overlays are a step beyond joins. While a spatial join merges the data tables of existing shapes, an overlay operation actually fractures and reconstructs the geometries themselves.
The documentation highlights operations like intersect, union, and clip. These tools apply classic Boolean logic AND or ATCH, not directly to spatial coordinates.
Let's apply this to the example provided in the notes, which is finding park areas that contain dedicated bike paths.
Right, so you have a polygon layer of large city parks and a line layer of a massive citywide bike network. How does an intersect overlay differ from just doing a spatial join between them?
Well, if you just ran a spatial join, you would simply attach the park's name to the bike path's attribute table. But an intersect overlay acts mathematically like a pair of scissors.
A pair of scissors.
Yeah, it looks for the exact locations where the vector line of the bike path crosses the vector boundary of the park, and it physically cuts the line at those exact vertices.
Oh, I see. So the software discards every segment of the bike path that falls outside the park.
Exactly, creating a brand new standalone shapefile containing only the overlapping segments.
So you can then instantly calculate the exact linear mileage of bike paths specifically located inside park boundaries. That's so powerful.
It is, and you find these destructive geometry tools grouped together logically in the software. In ArcGIS Pro, the intersect and clip tools reside within the analysis overlay toolbox.
And in QGIS, you access them by dropping down the main vector menu and exploring the geoprocessing tools submenu.
Exactly.
Now, the intersect logic is incredibly precise, but it requires physical overlap.
Yeah.
I want to push back on this limitation based on real-world scenarios.
Okay, push back.
What if our bus stop isn't physically located inside the school property polygon? What if it's situated, 2 blocks down the street?
Yeah. Well, an intersect tool or a standard within spatial join will completely miss that bus stop because their coordinate boundaries do not cross at all.
So how do we find what's nearby?
This limitation necessitates a shift from overlay logic to proximity analysis. We must introduce the concept of a buffer to measure what exists near a target feature.
A buffer. Okay, so a buffer is an algorithm that constructs a brand new polygon zone around an existing feature at a rigidly specified distance.
Right. Instead of merely selecting the school building's footprint, you instruct the software to mathematically expand a 1,000-meter radius outward from every single vertex of the school's boundary.
And the output is a completely new, expanded polygon layer representing a zone of influence.
Yes. And once that buffer zone is generated, you can take that new layer and run a standard spatial join against your bus stops.
Oh, so the points that were previously ignored because they were down the street are now successfully captured inside the expanded 1,000-meter net.
Exactly. The documentation points to the execution paths for this. In QGIS, you find this under vector geometry, then buffer.
And in ArcGIS Pro, it sits under analysis, proximity, then buffer. But there is a massive, mathematically dangerous catch highlighted in the notes regarding how this 1,000-meter distance is actually calculated.
Yeah, this is a big one. The danger lies in the difference between planar and geodesic distance measurements.
Planar versus geodesic. Let's break that down.
A planar buffer algorithm relies on basic Euclidean geometry. It assumes the surface it is measuring across is as perfectly flat as a piece of grid paper on a desk.
So it's just utilizing standard Pythagorean theorems to determine the 1,000-meter radius.
Right, and if you are working on a very localized scale, like mapping a single neighborhood using that UTM coordinate system we discussed earlier, a planar buffer is mathematically acceptable.
Because over the span of a few city blocks, the actual curvature of the Earth does not induce enough distortion to invalidate a 500-meter zone.
Exactly. However, if you apply that same planar algorithm to a global data set, the results become catastrophically inaccurate.
The sources use the example of a transoceanic flight path.
Yes. Imagine trying to buffer the flight path of an international airline. As you move closer to the poles on a flattened projection, the planar algorithm will stretch and distort the buffer zone into massive, inaccurate ovals.
Because it is trying to force a curved, three-dimensional reality onto a flat, two-dimensional mathematical model.
Yes. To solve this, the documentation states you must use geodesic buffering.
And geodesic algorithms calculate the great circle distance, right? Factoring in the actual 3D curvature of the globe to ensure the buffer remains a true 1,000 meters, regardless of its location on the map.
Correct. It is a critical distinction that requires you to intimately know the scale of your data.
The documentation actually notes that ArcGIS Pro often defaults to planar methods, but provides explicit geodesic toggles.
Yeah, and standard QGIS buffers have historically defaulted to planar based on the project's CRS, requiring users to seek advanced settings or plugins for true geodesic calculations on global datasets.
That's a really important technical nuance to keep in mind. So moving beyond vector proximity, the technical notes mandate that we explored the other side of the data coin, raster analytics.
Right, the grids.
We've spent significant time discussing algorithms that manipulate lines and polygons, but how do we analyze continuous grid data?
Well, raster analysis requires an entirely different mathematical approach because we are not calculating coordinates anymore. We are calculating matrices of pixel values.
Let's return to the digital elevation model, the DEM, which is a massive grid where every individual cell contains a value representing the height above sea level.
Okay, so if a city planner needs to identify dangerous terrain for a new housing development, just looking at a gradient of elevation values isn't enough.
Right, they need to know the actual steepness, the rate of change. How does the software transform a flat grid of heights into a localized map of steep slopes?
The software utilizes what is called a moving window algorithm, or a kernel.
A moving window.
Yeah, the algorithm isolates a tiny 3x3 grid of pixels. It focuses on the center pixel and compares its elevation value to the 8 pixels immediately surrounding it.
Oh, that makes sense. By analyzing the maximum rate of change in value across that specific 3x3 distance, it calculates the exact degree of slope for that center cell.
Exactly. The kernel then slides over 1 pixel, performs the exact same mathematical comparison for the new center, and repeats this millions of times until it has traversed the entire map.
And the output is a brand new raster matrix, where the cell values no longer represent height, but rather the degree of steepness.
Right. In QGIS, accessing this algorithm is incredibly straightforward. You navigate to the raster menu, select analysis, and choose slope. The system utilizes the underlying GDAL libraries to process the matrix math efficiently.
In ArcGIS Pro, this specific capability actually requires checking out an advanced license. The tool sits within the Spatial Analyst extension.
Yeah, you navigate to the surface toolset and select slope. The resulting dataset instantly highlights areas where the terrain is too steep for safe construction.
The documentation stresses a really profound implication here. Through raster math, you are generating fundamentally new knowledge.
You really are. The degree of slope was never explicitly recorded by the satellite that captured the elevation data.
Right. You have used geographic calculus to synthesize a completely new variable for your analysis.
And the sources point out that advanced users don't even need a graphical interface to do this. By utilizing command line tools like gdalcalc.py, you can perform raw map algebra.
Map algebra.
Yeah, you can write a custom Python formula that multiplies one raster grid by another, essentially doing matrix calculus on the physical geography of the Earth.
You can extrapolate this logic to virtually any continuous surface scenario. You can model the exact dispersion of a chemical spill through a groundwater matrix, or calculate the precise accumulation of rainwater flow down a mountainside by analyzing the comparative elevation values of millions of neighboring pixels.
It is genuinely a staggering amount of analytical power.
It really is. But I have to admit, reading through the documentation detailing EPSG projections, raycasting algorithms, planar distortions, and moving window matrix math, it feels like walking into a technical minefield.
It definitely can be.
Like a single wrong click could ruin an entire project.
The documentation totally acknowledges that reality. It explicitly outlines 4 primary roadblocks that consistently derail beginners.
We have thoroughly explored the first 2, right? Ignoring CRS mismatches, which fundamentally misaligns the geometry, and utilizing planar measurements on global datasets, which physically distorts the scale.
Yes, so let's examine the third major pitfall identified in the notes, which is confusing an attribute join with a spatial join.
I can see exactly how this happens in the interface. A user has 2 layers they want the data to merge, so they just hunt for a button labeled join without considering the underlying mechanism.
Right. And if a user attempts to run a standard relational database join on files that don't share identical key columns, the software will simply fail to find matches. You are left with an entirely empty attribute table.
But the reverse is even more destructive, right?
Oh, yeah. If you accidentally run a spatial join on massive data sets without defining strict intersection rules, you risk creating catastrophic one-to-many relationship errors.
For example, if a single large school polygon spatially overlaps with 50 different bus stops, and you aren't careful with your join parameters, what happens?
The software might duplicate the school's record 50 separate times in your database to accommodate every single point.
Oh, wow. Which completely ruins any statistical summaries you try to run afterward.
Completely ruins them. And the final pitfall documented is perhaps the most frustrating because it often originates from outside the software. Poor data quality and invalid geometries.
Right, because you might have your CRS perfectly aligned and your join parameters strictly defined, but the tool simply refuses to run, throwing a geometry error instead.
Yeah, that happens a lot.
What actually constitutes an invalid geometry in a vector file? I mean, if a polygon is just a sequence of x and y coordinates that eventually loops closed, how can the math behind it be broken?
The most common failure is a self-intersecting polygon, often referred to as a bow tie error.
The bow tie error.
Yeah. Imagine drawing the boundary of a park, but instead of drawing a clean circle, your line crosses over itself in the middle, creating a figure 8 shape before closing.
Oh, I see. That breaks the fundamental topological rules.
Exactly. When the raycasting algorithm or area calculation tool attempts to process that figure 8, it cannot mathematically determine which part of the shape is the inside and which part is the outside. The geometric logic collapses.
And real-world data, digitized by humans, is notoriously full of these tiny topological errors, alongside issues like null vertices or tiny microscopic gaps between property boundaries called slivers.
Yes, and because you cannot manually inspect millions of vertices, you must rely on the software's automated repair algorithms.
The documentation points directly to these built-in safety nets. QGIS features a dedicated algorithm in the processing toolbox called check validity.
Right. It systematically scans every single vertex in your layer, flags topological violations, and isolates the broken geometries into a separate error layer for inspection.
And ArcGIS Pro handles this through an automated geoprocessing tool simply named Repair Geometry.
When executed, that algorithm forces polygons to adhere to strict topological rules, automatically untangling bow tie intersections and deleting null coordinates to ensure the file is mathematically sound before analysis begins.
Running those validity checks ensures that the final step of our overall blueprint, visualizing and sharing the result, actually delivers truthful answers.
Because if your geometries are invalid or your projections are warped, your final map is simply presenting bad data in a highly convincing format.
When we step back and view this entire documented workflow as a cohesive system, the true value becomes so apparent.
It really does. This technical journey of defining problems, repairing geometries, aligning coordinate matrices, and executing proximity buffers, it is the exact infrastructure driving modern spatial decision-making.
It is the exact process environmental protection agencies utilize. They take vector polygons of vulnerable wetlands, run geodesic buffers to establish safe distances, and spatially join those zones against proposed industrial development parcels to prevent ecological damage.
And it is exactly how municipal planning departments ingest raw tabular census data, execute attribute joins to link it to specific neighborhood boundaries, and then utilize raster slope analysis to determine the safest, most accessible location to construct a new community hospital.
Whether the application is tracking endangered species migration using continuous environmental rasters, or optimizing a fleet of delivery trucks using discrete vector road networks, the underlying mechanical workflow remains identically rigorous and powerful.
The documentation proves that GIS is not merely a software category, it is a fundamental way of interpreting reality. I want to leave you with a concept to consider.
Let's hear it.
By mastering the spatial workflow, understanding the mechanics of coordinates, joins, and matrices, you are gaining the ability to expose relationships that traditional spreadsheets simply cannot process.
It transforms a massive wall of text and numbers into a tangible, interacting environment.
Exactly. Consider the data you interact with daily in your own field. What invisible patterns could a simple spatial overlay or proximity buffer suddenly reveal?
If you took your standard tabular business metrics and rigorously pinned them to a mathematical model of the Earth, what entirely new answers could materialize?
It's a phenomenal perspective to end on, because once you understand the hidden mathematics and algorithms powering these tools, you will never look at a flat, static paper map the exact same way again.
Absolutely. To explore the mechanics of these tools directly, please check out the description. We have provided links to the full technical appendix, the step-by-step documentation for configuring both ArcGIS Pro and QGIS, the official GDAL reference libraries, and the exact sample datasets we analyzed today.
Everything you need to start running your own spatial queries is documented right there.
If you found value in this deep dive into the hidden architecture of spatial analysis, please hit that subscribe button so you don't miss our next exploration. Thank you for joining us, and we will see you next time.